Quick, what kind of graph is this? It's a line, right? Wrong. It's your old friend, the sinusoidal graph, y equals sine of x. But the point has been proven, hopefully, that if you zoom in on anything enough, it can resemble a line. And that's the premise that we're using today, basically, to tackle one of the classic questions that drove the development of calculus for Isaac Newton, the German mathematician Leibniz. Those are the two that are most closely associated with the invention of calculus, if you will, because Newton, as I'm sure you know from physics class, had his laws of motion, and interested in gravity and the apple falling out of the tree, all that jazz. And he was really interested in finding the rate of change of a curve at a split second. And a curve doesn't have a rate of change. A curve doesn't have slope like a line does. A line, the slope stays the same no matter where you are. But he thought that idea of, if I zoom in enough, I'm sure he didn't think the phrase zoom in, but if I look at it closely enough, at 2 points super close, it could resemble a line. And maybe like this, like maybe just any curve is just a lot of little tiny infinitely small line segments just chopped up, and each one has its own slope. And everywhere you go, the slope is slightly different until you gradually get the full picture of that curve. So here's what we're going to do. We're going to start with y equals x squared, and we're going to do this on paper in a minute, but this is a really nice demo on Desmos to help you visualize the math that we'll be doing. And on the graph of x squared, I'm going to pick a point at 2. 2 is a nice point here. So I'm going to pick this right here. Okay, now if I wanted the slope at this point, the slope of the curve, I mean, if I zoom in on that spot, it's definitely, a positive slope, a positive rate of change. But anywhere I pick another point, it's not really, even if I zoom in super close, it's still just a curve. And so anything I do will really just be a very good approximation of that instantaneous rate of change. And this is what bothered people. How can I find the slope using 1 point? Our slope formula depends on having 2 points. So here's the idea. At that point, we draw a tangent line, and the tangent line kind of captures the rate of change of the curve at that split second. The slope of that tangent line is the slope we're looking for, the slope of the curve. And as I move the a value around, the tangent line goes with it. So you can kind of see it every split second. Everywhere I'm at the curve, it's a new tangent line, it's a new slope. Even though if I go pretty close, not a big difference maybe between that line and that line, but they're different. And obviously, more I move around, I get a steep slope. So I'm sticking with this. But we're going to start with our classic old Algebra 1 formula of, slope is y2 minus y1 over x2 minus x1. I need a second point. So you don't want to rely on, using a second point on this line, because how do I know it passes through this point if I don't have the equation of the line? If I had the equation of the line, I would know the slope. And I don't want to estimate like it looks like it goes through that point. Let me find it. So the goal is really to do everything in terms of x squared. I don't want to rely on this line I've drawn. That's really just a visualization of the slope I'm looking for at that second. So I'm going to put a second point on the curve. And I'm going to bring it into view a little bit here. And you don't have to get too caught up in the notation over here on the side, but if you'll notice this, A is the purple point. That's the 2 that I started with. And this second point, this green point, it has been called A plus H. So A is 2, and that's the purple point. And this is 2 plus a little bit, And right now that H, that little bit, is 2.4. So right now it's at 4.4, and its y value would be f of A plus H. And you know, if I want to think about the slope between these 2 points, that would be y2 minus y1, x2 minus x1. You'll see that more in depth in a minute, but here's the idea. Now, if I connect those two with a line, that slope is positive, and so is the slope I'm looking for. But that's not a great estimation of it. It's maybe decent, but I feel like we can do better. And it will look more and more like the tangent line that I'm really after the closer I bring that second point to the point of tangency. So now this point, this a is at 2. I'm not changing that. That's the point I really care about. But the a plus h, I'm making the h smaller. And that h represents the difference between this x value and this x value, the x value of the green. And as I whittle down that difference, it closer and, you know, it more closely resembles that tangent line. And this is just like the average versus instantaneous rate of change that I was trying to make a point with on the worksheet yesterday. You know, if you have 2 points far apart, you know, and I traveled, you know, 20 miles over the span of an hour, okay, my average was 20 miles per hour, but how fast was I going at 45 minutes in? I don't really know. But those wires on the ground that are used to measure your speed, they're doing an average rate of change, but they're doing it with the wires so closely together that it's practically the instantaneous rate of change. And that's the idea we're going for here, is that the closer I bring that second point, the more closely, the better estimation it is, until I'm basically right on there. So what I'm really after is not an estimation, though, is the perfect slope, and that is what limits are all about. That's what this whole development of the language was, because it didn't exist, and they needed a way to describe, how do I bring this point infinitely close? In other words, how do I make it approach? How do I make this h, this difference between a and this second point, how do I make the difference approach 0? Because once it gets to 0, I can't actually deal with it, because now I'm back to where I was. It's just 1 point. So that's what I really want, is that concept of what's the slope between these as h approaches 0. But now that we've put in all the work on limits the last, you know, week and a half, 2 weeks, now we've got all the math we need to make it happen. And that's why limits were so important. That's why they're the start of calculus. They had to literally invent that notation, that language, to describe these ideas of things in motion and things becoming infinitely close and what they would be approaching as a value. So that's what we're going to do on paper right now, but hopefully just this visualization of, hey, we're going to set up the slope between these 2 points, and then I'm going to take the limit as h approaches 0. And when I do that, that should be the slope of the tangent line. That's a beautiful thing, kids, and that is probably the most important problem in calculus right there. That's what kick-started it all. So let's do it now. All right, let's take that next leap as calculus students. Okay, so now we're off the computer and onto paper, but we're right back in the same spot we were just looking at on the graph of y equals x squared, trying to write the equation, or actually trying to find the slope of that tangent line at x equals 2. So here's that line. Trying to find the slope of that line, which is not perfectly tangent. There's some human error there. But again, here is the idea. We're going to use the formula for slope, and we sort of picture this point as being 2, comma, well, you know the y-coordinate is 4 because it's x squared, but just for right now I'm going to call it f of 2, because regardless of what function I was, you know, dealing with, if x is 2, the y-coordinate can be called f of 2. And so we pick a second point, you know, this theoretical point, the one that I'm going to move closer to it, and I'm going to call that second point 2 plus h. right? Instead of just calling it another value altogether, I want to call it something in the neighborhood of this. So 2, but plus a little bit. And therefore the y coordinate I can call f of 2 plus h. And the slope of that line will become a better and better approximation the closer I bring this second point to my point of tangency. Or in other words, as I whittle down this value of h, this difference between here and there. So, but the idea is just setting up the slope between these 2 points. So watch what we're going to do here. The slope at x equals 2. This is what we're finding. I'm going to set up the slope between these 2 points. Just using my old y1, y2. I'm leaving a little space here, as you'll notice. But y2 minus y1, f of 2 plus h minus y1, f of 2. Of course, you could have gone in the opposite order, and that would be fine. But in the denominator, 2 plus h minus 2. Now that would be the slope between these 2 points, but it doesn't become the slope of the tangent line until I bring it infinitely close, or in other words, as that h value approaches 0. So I'm going to take the limit of this as h approaches 0. And you'll notice one thing that happens right off the bat is in the denominator, the 2x values will always cancel out. It doesn't really matter what they were initially, 2 and 2, 7 and 7, but they're going to cancel each other out, and all you're going to be left with is h. And that should start to look pretty familiar in terms of things we've been doing. That's why this is called the difference quotient, or the slope quotient, as some people call it, because it's been derived just literally from rise over run. And so just to generalize what I'm doing here, I'm trying to find the slope of the line tangent at that point, because that slope of the tangent is the slope of the curve. And if I want the slope at a particular spot, you know, if I want at x equals c, maybe I should have gone with a, but it doesn't really matter. The idea is I set up the slope between f of c plus h minus f of c over c plus h minus c, but they will always leave you with h. And I take the limit on this as h approaches 0. And of course you can see just from your limit work, if I try to directly substitute 0 in here, I get 0 in the top because it'll be f of c minus f of c over 0, which is when you bring it right on top of that point, yeah, it's now just the same point and you're stuck. So that's why you've got to use all your limit techniques. So here's where we're going to get specific to this problem. Here's the setup, but now I'm going to use the equation f of x equals x squared to set up and simplify this. Now, I know this slope is going to be positive, but anybody got any guesses for it? I don't know. What do you think? You can think something in your head. And now we're going to actually find it. We're going to actually calculate this slope, which is pretty crazy if you think about it. Now, f of 2 plus h, for this function, f of x squared, means you're doing 2 plus h squared minus f of 2 all over h. And now 2 plus h squared, that's a binomial here. I guess I'm still taking the limit. I should have that out there. 2 plus h squared is going to be 4 plus 2h plus 4h plus h squared. Minus f of 2, and f of 2 is, of course, 4. Which, of course, is, we knew that was just the y coordinate at that point. Minus 4 all over h. And look what happens, as should always happen. Anything without h cancels each other out. So I'm left with this over h, and that means I can factor h out, cancel, and now h cancels, and now you can plug in 0 for h. And when you plug in 0 for h out of what's left, you're left with 4. The slope of that line is exactly 4. That's the slope of the curve at that moment, the instantaneous rate of change. And if I wanted it at any other point, I would just redo this setup but instead of using 2, I'd use whatever x value I was interested in. So it's really pretty far out to think that you can do something like that. But now that you have limits mastered, it should make sense. We go to all that hopefully all that trouble of showing the demo so that you really kind of understand what you're doing. You know, you could just slap this in front of you and say, hey, memorize this and this is how you do it. But I think it really helps you to understand it. And in calculus next year, you know, when you do some different things here and there and some variations on this, hopefully you'll understand where it came from, and just helps it stick with you that much better. So we're just going to see a couple different things. They're going to just change the curve up a little bit, change the x values, but now we're going to go one step further. We're not just going to find the slope of the curve at that moment or the tangent line. We're actually going to write the equation of the tangent line. Getting the slope is the hard part. So now that we know how to do that, it's fine. But just keep in mind, if you want to write the equation of a line, you need two things. You need to have at least one point on the line, and you need to have the slope of that line. And I'm going to write the equation using point slope form, and this is really where you can hopefully get on board with that. If you haven't, you can use any form you want, but this is going to be the fastest. So kind of like, you know, you resisted radians at first, but then you all came around on it. So let's just see here. So number 2, write the equation of the line tangent to f of x equals root x, which is right here, that nice square root graph, at x equals 4. Now you have the graph in front of you, but that's really hopefully just to kind of convince you of what you're doing. Let's try to do it all with algebra. Now the point, I need two things. I need a point, I need the slope. The point, how would you find the y value if you didn't have the graph in front of you? You would plug 4 into the function. Oh, 4 square root of 4 is 2. So your point is 4 comma 2, and we can of course see that. That's the point, 4 comma 2. But now let's try to write the equation of that tangent line. I know it's got a positive slope, but how positive? Let's find that. That's the real calculus work. So the slope is going to be this. We're going to take the limit as h approaches 0. And what I'm going to do is this setup again. If I'm talking about at the x value of 4, then I'm doing f of 4 plus h minus f of 4. That's the key x value that I care about in this problem. So it's all about in that neighborhood of 4. And again, the idea is picking a second point on the curve and calling it 4 plus h, and the y-coordinate being f of 4 plus h. Setting up the slope between these two and bringing it infinitely close. So for this particular function, f of 4 plus h would be plugging this into the square root graph. That would be the square root of 4 plus h minus f of 4. Now f of 4 is that y value we already found, 2. All over h. Hey, is this starting to look familiar? How do I do this? I'm going to multiply by the conjugate. Hopefully these are feeling, you know, kind of autopilot-esque. You've been grinding it out, and now that you need it, this part can come easily, hopefully, to free up your mind to handle the concepts, the larger ideas of what you're doing. So now you multiply out that top, you'll have 4 plus h minus 4 all over h. Leave that denominator factored, right? This is easy, this stuff now, right? The 4 minus 4 cancels. You're left with h over this, which means h can cancel, leaving you with 1 in the numerator. And now you can plug in 0 for h. And, you know, just be careful when you're doing this that you don't make a silly mistake. There's a lot of stuff being canceled. So plugging in 0 there will be root 4, which is 2, plus 2, which will give you 1/4. What did I just find there after all that work? That is the slope of this line. So now I know the point, 4 comma 2, and I know the slope. So if you have the point and the slope, I mean, doesn't point slope form seem the easiest way to write it? And here is point slope form. It would be y minus the y coordinate of the point equals the slope times x minus the x coordinate. And remember, that just really comes from your formula of, y2 minus y1 over x2 minus x1, and just cross multiplying it to move this quantity over to this side. That's where the point slope form comes from. If you want to do slope intercept form, be my guest. But you're going to see in calculus you do a lot of things with radicals and trig functions, and sometimes the y coordinates and the slope are things like root 3 over 3 and pi, and you don't want to try to change it around. Just plop it into point slope and move on. And one more now, just in case you want to see it with a rational function here, but you've kind of seen the whole trickery now, that we're going to write the equation of the line tangent to this graph at x equals -2. So just for a little visualization, here's where we're at on this curve. That slope is going to be negative. The function is decreasing here, so it's going to have a negative slope. But what is that y coordinate? Let's get the easy stuff first. What's the point? So f of -2 is -1/2 when you plug that in there. So there's your point of tangency, -2, -1/2. It seems to be good by this graph. Now let's find the slope. Limit as h approaches 0, and we're doing f of, and I guess I'll write it out. It's the first day. I'm not going to take too many shortcuts. It's f of -2, that's the x value you care about, plus h minus f of -2, all over h. What does that mean for this function in particular? And if you can start right off in this step right here in your work, I'm totally fine with that. So if you plug -2 plus h into this function, it will be 1 over -2 plus h minus f of -2, which is this y value. So minus -1/2 will be plus 1/2 all over h. And now I've got my classic complex fraction. Can't plug in 0, I'll get 0 over 0, indeterminate form. I'm going to multiply the top and bottom by the LCD, which would be 2 times -2 plus h, or if you prefer to make common denominators and add them together, be my guest. I don't, as long as the algebra is good, I'm fine with it. In the denominator, we get 2h times -2 plus h. Don't forget that. And the top, -2 plus h cancels, leaving us with 2 plus the 2 cancels here. So we'll get plus 1 times -2 plus h. So positive 1 times this will give you just -2 plus h. What happens? 2 minus 2. You're left with h over h. Gone. Meaning now you can plug in 0 for h. Remember, you have 1 here because everything canceled out here in the top. So I'll be left with 1 over 2 times putting 0 there will give me -2, and that will give you -1/4. So that slope is -1/4. That seems to be reasonable. It's negative. It's kind of flat, -1/4. So you got your point. You got your slope. Here we go, point slope form. Y minus -1/2, so y plus 1/2 equals the slope times x minus -2, so x plus 2. Done. Move on to other problems. All right, so that's a big day, kids. A lot of stuff, a lot of big ideas to unpack with calculus. Hopefully it made sense. If not, ask questions and keep at it and you'll get there. Have a good day.